Somebody asked about an LED source, and oh, okay. In the previous lecture, a question about LEDs sources was brought up, and Scott Prawl gave Jonica and I the geometry, so I will be able to add it to our arsenal. Another thing. Oh, okay. Another thing that a question was about MC MATLAB, and actually, their paper is on the web, and it's from a Danish group, and they base it on MCXYZ, the code. So they ported it, I think, to MATLAB, and that is a Jacques Lee and Prawl code. So hopefully, yeah, that's all good. That's all good. So I just wanted to, I did a little, after your questions, just wanted to do a little homework. And okay, so let's see.
Might have to bend it in her direction a little bit.
Okay, is this good? Okay, closer. Okay, I don't want to be too loud, but. Okay, so my talk will be on the determination of tissue properties from optical signals. And so you've seen that our field is a lot about diagnostics, is determining the characteristics or the structure of tissue from some sort of measurement. And this can scale. So the group Giacomelli and his lab, they used, thanks. They wanted to determine single scatter size and shape. Sylvain Joux looked at thicker tissues like the hand, and then Brian Pogue's group are looking at not only figuring out the optical properties of a breast, but also the tomography, where spatial volume segregation of that breast, and where the optical properties, what are the optical properties in each of those volumes. So because these different spatial scales are being investigated, the models have to follow suit. So Giacomelli used me and T matrix scattering functions. Sylvain Joux used Monte Carlo solutions. You heard about delta P1 solutions. Brian Pogue's group used standard diffusion. So hopefully in this talk, I will go over the chi-squared minimization. I'll go over some optimization methods, and then we'll look at actual inversions and see what happens in them, what went wrong, why didn't you get the right answer. So you've seen this chart a lot. Go over it very quickly. You have a set of optical or physiological parameters. You have a model function, and you use it to determine predictions of measurements. But the inverse problem is you take these measurements, you use some sort of model, and then you get back the parameter predictions. This inverse problem is ill-conditioned, meaning there could be several parameter predictions that give rise to the same set of measurements. So your choice of measurement, your choice of model function, and the quality of your measurements can affect your success. So at the root of a lot of inverse solutions is something called the chi-squared equation. And we try to minimize the chi-squared. You can see here, it's given by this equation 1, where the y hat are your measurements. You have m of them. Y is your model function, and it's a function of your vector A. These are the parameters you seek to find. And then this equation is divided by the standard deviation of the measurement. This is a weighted chi-squared. You do not need to have this, but it's helpful because if there is noise in your measurements, you can imagine that if the standard deviation is large, it deweights that particular component of the summand. So it kind of puts them on a more level playing field. This equation is based on the maximum likelihood estimation, and this development of this equation relies on two assumptions: that the measurements are mutually independent and that the measurements are normally distributed about a mean that's the model function. Okay, a lot of times we violate these, and that also can have effect on your success. So let's break this down. I show in Y hat in blue. One of the questions that has come up that you want as many measurements as unknown. You're going to have a hard trouble. There are problems that this occurs, and I will talk about that later. But in general, you have a certain set of equations, certain set of knowns. It's helpful if the measurements that you have is greater than the number of parameters you're trying to find. Are the measurements at locations and times that are sensitive to the changes? For instance, if you are looking at a very close source detector separation, but you're expecting to measure a change to something deep in the tissue, that detector measurement may not have information about the light that has made it down that far, that sort of thing. Rolf showed some time dependence. You just want to make sure that you're putting the windows of where you're picking out the data in the right place. Is there redundancy in the measurements? Sometimes you might have a lot of measurements, but they're all interrogating the same part of the tissue. You want to be able to sometimes interrogate different parts so that you can kind of tease apart the parameters A and how the measurements were calibrated. So in green, I show the model function. We talked a lot about having the model function be accurate for the measurement domain. So standard diffusion, you really have to have scattering much greater than absorption. You can't use it close to the source, a detector close to the source. And is the model function sensitive to parameters in A? So again, standard diffusion has no knowledge of G anisotropy, so would not be a good model to use to try to determine anisotropy. You also want these models to predict a forward prediction fairly quickly, because a lot of the methods we use to solve inverse problems are iterative in nature, and what you're going to have to do is provide the yi prediction as the vector A changes as it moves through its improvement in the iterative scheme. So you want to make sure that you can provide a fast forward model prediction. And sometimes you need to integrate. So standard diffusion, again, gives you reflectance at a point on the surface, but maybe you're actually measuring a finite domain. So you have to integrate that solution over the finite domain that you're measuring. And if you do have this measurement error, then it's nice to use within this chi-squared, but is not necessary. So the model function, oh yes.
Like in your measurements, do you generally use
Chi-squared?
Yeah,
so the chi-squared is just a mechanism that is used to solve the inverse problem. In it is the model function. So the model function is your choice within that, and then it gets plugged into the chi-squared function.
Do you think it gives more accurate results than using simple squares?
Well, it is a least squares in the fact that yeah, I mean it's just it's okay. Yeah, it's just if you take away the error, then it's just a least square. Yeah, yeah. So for your
have a difference between model and expression. This should not contribute as much to the square as other measurements in the data set that are very small. So incorporating the error is an important weighting factor that, you don't arrive the optimization to a domain to sort of fit data points that we actually have. So
Well, if that substitute, can that be used as a substitute for, let's say, regularization or something? Because regularization does something with the noise too, right? Like,
regularization is it's an additional constraint. I don't think they're mutually exclusive. Both regularization and error, but I think they're two different data lines.
I actually go over those equations later, so the regularization, yes.
I also have a question about the error. So here is the error measure. So are we assuming that we are measuring the same thing like a couple of times to be able to calculate?
Sometimes people do that. They take the same measurement 10 times and create their own measurement error. Sometimes there's an entry to the error that you have to know in your measurement, and you can add that in. Yeah, so. So when you think about your model, you have different options available to you. We've talked about the standard diffusion. It's nice because there's an analytic solution. You can plug in the optical properties, get the result for reflectance, for homogeneous, layered. They have one for a sphere, but David Bow has created analytic solution for an embedded sphere. But you do have this assumption on all the solutions that scattering is much greater than absorption. As you reduce and you have to be, far away from the source. As you reduce your spatial scale or your absorption increases, then you have to go to higher order PN solutions. And then if you have very complex tissue definitions, then Monte Carlo is the gold standard for that. You also have to pick your measurement domain wisely. We're all covered, spatially resolved versus spatial frequency. Tomorrow you'll hear about time resolved or temporal frequency. There's also the issue of wavelengths, which ones to use, and any combination of the above. And then also, it depends on what you're looking for. Are you looking for optical properties? Are you looking for chromophore concentrations? Are you looking for scatterer size? All of these kind of come into play as far as picking your model function, what's going to work for you best to invert that measurement. So I'm going to go over a few optimization methods. The methods that I chose were driven from the ones that are used under the hood in the labs that you're doing this week. So this lookup table is one that you'll see this afternoon for spatial frequency domain lab. It's also, when David gave his talk on modulum, it's the basis of how his instruments work. This Nelder-Mead simplex method is what's under the hood in the integrating sphere. Levenberg-Marquardt is what's under the hood when you do tomorrow at the temporal frequency lab. It'll be the code that's underneath that. And then I'll just briefly go over some a neural net solution. So in the table lookup, you basically take the mu A and mu S prime values that you feel are representative of the tissue that you're trying to invert or solve for. So you get this range of mu A, you get this range of mu S prime, and then you create forward predictions for all those values, all the combinations and permutations, create a forward table. And then you use this forward table to look up what the optical property says. So I think the best way is to look at this picture here. It's kind of hard to, I probably should have blown it up, but so along this x-axis is reflectance for spatial frequency 0.5 inverse millimeters. Along this y-axis is diffuse reflectance for a spatial frequency of 0. And then these are isocurves of constant mu A and mu S values. Okay, so David Kucha generated his range of mu A and mu S prime, and then he generated forward predictions. That's all of these in here. And then so now when he takes the measurement, he says, at spatial frequency 0.5, I measured this spatial frequency 0, I measured this. He can just come into this table, say, mu A, mu S prime are these values. Yes. Yes. Homogeneous. Yeah. It's a little dicey. It's like, yes.
And the density of your liquid just has to match whatever precision your system measure.
Good question. Yes. So David told me that you have to kind of figure how smooth the data is, and you'll need to add in more data in between so one way is you could just interpolate, but he said a lot of times he added data to divvy up that space in its curvature better. Yeah. So it's really easy to implement. It's a nice aspect about it. One key assumption is that you have to have a unique set of parameters for any set of measurements. Otherwise, you're going to go into that table, have multiple, then you're not really solving it. So that's kind of key. And that's where I think that we did have talks early on when David was first generating his tables for his thesis, that he was trying to look at layered geometries, and that gets very complicated fast, ill-posed fast. So you notice on that picture with David, of course, it's perfect. It looks pretty orthogonal. Those isocurves with mu A and mu S prime are pretty, orthogonal. I did some work with Darren Roblier's group at Boston University, and I chose different spatial frequencies. So this is 0.3 along the x-axis and 0 along the y. You can start seeing how that orthogonality is starting to break down. And then if you look at 0.3 along the x-axis, 0.2 along the y-axis, now you've got something pretty flat. It's collapsed upon itself. It's really going to be hard to pull out what your mu A and mu S prime are here. So that is all I was going to talk about lookup table. Now I'm going to describe the simplex method. This is what the integrating sphere code is doing. This is kind of a fun method in that you say you're looking for mu A and mu S or mu S prime, doesn't matter. So you're looking for two parameters. Then what you do is you create a geometry of a geometric shape of 3 with 3 vertices. So it's easy to see here as triangle. So if you had 3 parameters that you're seeking, then it would be quadrilateral and so on. So it's a fairly general method. But let's keep it simple. We're looking for mu A and mu S. We've got 3, we just take 3 initial guesses, like just say, okay, let's try 3 initial guesses. And we determine the chi-squared. So you have your measurements, you have your model, you determine your chi-squared value at these 3 vertices, and then you order them. Okay, so we're all trying to get to smaller chi-squared. So you order the chi-squared, you take away the biggest one. So let's say it's V3 here, you take away that. Then you find the center of gravity. That's just a weighted location between these. And you flip this thing. So you reflect it. And there's these parameters you use to reflect it. You check it, how the chi-squared is in this new position over here. Sometimes you have to contract, move the position closer. Sometimes you expand, you move that position out. And you're all just randomly trying to find where are you reducing your chi-squared. Sometimes you reduce the whole triangle. So there are typical values for these reflections, contractions, expansions, and reductions that are given here based on the equations I gave on the previous chart. And so I show here, so this is a little schematic of my chi-squared space where I'm looking for in this case, mu A and mu S. And this shows you, we're trying to find this minima here in red. There might be other minima, but this is the global minima. And these actions try to move this triangle closer and closer to this trough or this sink, this bowl area. So you'll see in an animation what's going on here. Make this full screen. Oops. Let me try this. Okay, oops. Let me do that. Okay. So you can see how it's doing these triangles. It's reflecting, it's expanding. There might be a contraction in here one of the times. And it's trying to get to that bowl, the deepest part where the chi-squared is the smallest. Yeah, there's a contraction. Still going, still looking. Okay. Some of the drawbacks of this method is if you start off with 3 initial guesses, in this case 3, in a really small area, you might just kind of move around in that area. It could lead to a very localized search. Another negative part about this method is that it can converge to locations where the derivative is not 0. And that's kind of a problem because if you had, I mean, the good news is you don't need a differential information here, but the bad news is you didn't necessarily get to the minimal position. So now I'll move on to gradient-based methods. Yes. A lot of times it's random. You want to, I mean, sometimes you have kind of a intuition about what, of course, in the tissue that you're looking at based on the wavelengths that you have an idea of what range those optical properties should be in, and that's probably a good initial guess. Sometimes, and I'll show you in another case, we actually, this is a student in Vassen's lab, we were converging to local minima a lot. So what we did is kind of like the table lookup, we determine a span of viable mu A and mu S, and we just randomly kind of chose in those pairs, and then we started those as initial guess to see where they ended up. I think we took 10 initial guesses. This is work with Brian Hill in Boston's lab, and I'll show you. I think I have a chart on that.
Let me just. So there are 2 instances. You have cases where the inverse problem is and so in this case, we have that. So in those cases, you need to in other cases, the reason why but the intrinsic topology of the space is those cases that Look at where you converge based on a whole bunch of different that's to see if there is definitely has much lower chi-squared than the others, and it's just difficult to get to because the other thing just to be aware of is initial noise often has the effect of making the topology of these spaces. So sometimes if you have you think especially complicated.
It's complicated, but we, in a later chart, I'll describe how you can actually figure out, is it the measurement noise or is it the, yeah, is it Memorex? Yeah.
And relative to that, you guys check on the confidence region or where you end up in the confidence region to see if the initial values are I guess more accurate ones, or do you like do kind of like a look through it to see like if you get it to a better confidence region again?
A lot of the methods that we use will provide a confidence interval around the converged values. So if you're looking for U and S prime, you'll get, is that what you're asking? There would be a confidence interval given to give you, yeah, how confident am I in these results? And yeah. And sometimes those confidence intervals are so large that you're like, well, gee, I didn't really learn anything here. So yeah.
So if you get like a large confidence interval, you then check a different set of initial conditions?
You could. But that was more to getting to the minimum. It also kind of depends on the topology of that chi-squared. If it's really steep, then that confidence interval is going to probably be smaller than if it's a flat bowl. Then yeah, you might have a larger confidence interval. So on gradient-based methods, I'm going to start off with just a description of Newton-Raphson method. You might have used this in a numerical analysis class where you take a function, you're trying to find the root of the function. So you start with an initial guess, you determine the function at that initial guess, determine the tangent or the derivative of the function at that point, and then find where it intercepts. And this is your update. So you're moving closer and closer to this root here. So in the first step, you take your initial guess and you subtract off these to get this. It's basically just figuring out how you determine this A1. And for a general A n plus 1, you take the previous step and you subtract off the function at the previous step divided by the function derivative at the previous step. So in our case, we're trying to minimize the chi-squared. So we're looking to find when the gradient of the chi-squared is 0. So the gradient is this vector here. It's given, I give all the details here. It's straight differentiation. It's based on the number of, has dimension of the parameters that you're looking for here. So we have P parameters we're looking for. And because we're using that Newton-Raphson, that's the function, we need to take the derivative. So we take the derivative and it's called the Hessian. This is the second derivative. It's got the second derivatives of each of the parameters along the diagonal. On the off diagonal, it's each of the parameters taken 2 at a time, the second derivative, cross derivatives, and just the equation is here. Again, it's just straight differentiation of that chi-squared based on your A, ij, or jk here. So if we take these matrices, the update rule now, just because we're dealing with matrices, not that simple function, is that you're looking for your vector A at step n plus 1. It's equal to the vector at n minus 1, previous step, minus the Hessian inverse, and then you apply the gradient. Okay, so this is the equivalent of f divided by f derivative. Oh, yes.
Can we use the first, or would that be easier?
Yeah, it would be easier, but it would be easier, but we're the objective function, so the f in the Newton-Raphson is the gradient.
Oh,
Yeah, see, we're trying to find where that gradient is zero. So like the roots of, so that's our objective function, which means that, yeah, we have to deal with this Hessian thing, which gets kind of crazy, but not so crazy when it's just two parameters. It's a 2 by 2. I actually did it in my thesis 2 by 2. It's nice because you can invert a 2 by 2 and quickly. So yeah, I try to put the equations up in full glory in case people are dealing with bigger dimensions and things like that. So, but it does kind of create an imposing equation sometimes. Okay, so the Levenberg-Marquardt uses these concepts, but steps it up. So it combines something called the steepest descent far from the minimum and inverse Hessian near the minimum. And the way it works, to describe how it works, I'm basically just setting A equals 1/2 the Hessian, beta to minus 1/2 the gradient. And you can write that system of equations as kind of an AX equals B. So that's equation 9. And we're solving for this delta A. Okay, so this, what the Levenberg-Marquardt does is it takes the diagonal elements, just the diagonal, and multiplies the diagonal elements by this 1 plus lambda. Okay, so here's what it looks like in matrix form. You've got these diagonal elements. That's all, the only ones that have this 1 plus lambda. You have your, so this is your A prime, if you will, because it's not, we've changed A. We have our A's that we're solving for, and here's our B or beta. Okay, so the way this algorithm works is that you, again, choose an initial guess, kind of key, and choose an initial guess, and you compute your chi-squared. And then you set lambda along the diagonal to 0.001. I've had really good luck with this, these values that they're suggesting in this algorithm. So you set it to point, so you're multiplying all those diagonal elements by 1.001, slightly, changing them. And then you solve for your delta A. You compute your chi-squared at that step, so that's your n+1 step. And did you get better? Maybe you didn't. Maybe you moved to a place that didn't improve chi-squared. In that case, hit that lambda by a factor of 10. So now that diagonal is going to be hit by a factor of 1.01. Okay, so and we're going to, if you keep on doing this, go through that loop, you're going to be hitting that diagonal with factors of 10, and it'll get above 1 at certain times. Basically, what you're doing is you're making that matrix diagonally dominant. If you take it to the limit, you can think of the identity matrix. Identity matrix is easy to invert. And that's basically what it's doing. It's making that diagonal play a bigger part in the solution. If you did go to a smaller place on that iterate, then you decrease your lambda by a factor of 10, you move to that place, and then you repeat. And when you stop is when 2 successive iterates are less than a predefined epsilon. That's how they stop on this convergence. So sometimes in this method, you're just using the gradient method, gradient in the information. So if you're here, the gradient is going to tell you to go down into this region. And so it can get stuck in local minima. And this is getting back to your question, Anna. What we've done is figured out the parameter space of the parameters that we're looking for, viable ranges, and then you can just randomly select initial guesses and see, some are still going to go to that local minima, but some will make it in to the global. You could also use something called simulated annealing. Simulated annealing is something that uses the gradient most of the time, but once in a while it says, let's go to a higher chi-squared, and it will actually get you up and over some of these humps. But you can get stuck in a pathological curvature, and I'll describe more about what a pathological curvature is in subsequent slides. Because we've kind of got all set up with the Hessian and all these equations, we're going to go to optical tomography. So this is an instrument by Brian Pogue's group. It's to create a topological map of a breast. The woman lies prone. There are 16 sources, 16 detectors, so we have 256 measurements that surround the breast. And they created phantoms. So just to be clear, they're segmenting the breast into different regions, volume regions, and in each of those regions, they're trying to find the optical properties, okay, with these 256 measurements. So they have used phantoms where they knew exactly where the changes to absorption and scanning are, and then here are the reconstructed images. So now we're looking for a 3D spatial map of optical properties, which means the chi-squared is going to have another summand in here. And so you're going to have I actually changed this to be S times M. It is X times N, but it's not dimension S times N. S times N measurements now, in his case, 256. But the parameters A now are describing the mu A and mu S in a segmented tissue volume. And in the breast, it's thousands. They have thousands, and you're getting mu A and mu S. So very ill-posed problem. Definitely the measurements are far smaller than the number of parameters that you're seeking. So they use regularization techniques. So how is that formed? So you write the chi-squared equation. This is the one on the previous page, and just in matrix form here, equation 14. Okay, so that's, well, that's this equation, but I had it filled out on previous slides. Okay, so then we take the derivative of the chi-squared and we ignore higher order terms. This simplifies it. So we end up with something that looks like equation 15. This J now is the Jacobian matrix, and it's the derivative of the model function at all the derivatives. And so you can solve for delta A in this equation, pull it over to the left-hand side, and you end up with something like this. But what you have over here is something highly, you need to take the inverse of this thing in curly brackets. And that's a tough thing to do. So what Tikhonov regularization does is it kind of like the Levenberg-Marquardt, just along the diagonal, it adds a lambda factor. And this is called the regularization factor. Sometimes it's a scalar, meaning it's the same lambda along the whole diagonal. But in Brian Pogue's case, they actually varied the lambda based on the tissue segment that the elements of the matrix were pertaining to. And then they solve for delta A, either using Levenberg-Marquardt, or sometimes they just invert the matrices. Yes. What lambda value you use? Good question. I think you could probably start off with a value. Again, you're adding on to the diagonal elements this identity times lambda. I would probably start off maybe similar to the Levenberg 0.001 see how that works and move on to see, because and like the Levenberg, you might get to a value greater than 1 here where you're adding in. So yeah, that's a good question though. I personally haven't had any. I've done the Levenberg. I haven't done the optical tomography personally, so I don't have any personal reference about a good choice on that.
I read a paper once. I think you can use different things, but on a paper that I read, they used the L curve. Maybe you could look that up. I don't know how applicable to that. I'm still trying to get, but you can look that up. They just image like measurements and then signals, like stuff that you can get from the detectors. And then like a curve appears, and then you choose where the curve looks most like the edge of the L. But
Huh.
they're like different measurements.
Okay.
They're like, but I don't think, yeah, I think everybody's like trying. I don't know how that one's, yeah, it's just what I read.
Thank you. L curve. Yes.
Yeah, doubt question. When you have multiple source and detectors, you're basically modeling it. How would do you consider the light intensity from other sources being captured as detectors? Do you consider that or cancel it out or add it in?
Okay, I'll take a stab at this answer because I think I might know, but I might need help. I think a lot of times he's wondering if you have the sources in this particular geometry, how do you keep away other sources of light into the fact that they might get detected by the detector? And a lot of times I think, at least as I've seen in optical setups, you put some sort of curtain or something where you block out other sources of light to your detectors so that you are sure that anything that's coming into the detector is solely from one of the sources that you set up. Is that fair, or what do you say?
I was considering in case of the breast.
Yeah.
You would light up the sources all around, right?
Yeah, you light them up, they surround, but I think, see how it looks kind of like it's.
One fiber, you detect, you need another fiber.
Oh, is that what you were wondering?
You don't illuminate all the sources simultaneously. Illumination.
I see. Is that what you were wondering? I thought you meant like sources of like
yes,
outside the system.
So I know that they will do sequentially, but so you're grabbing from all detectors, right? So I was wondering, how do you consider that the one from the farthest point to the closest point?
And you consider what?
So you have detectors all around with the
Yes.
sources. Now when one source is lighting, you're detecting from all the sources. So when you're modeling it, how do you?
No, you're detecting from the single source. You detect all the detectors from a single source.
Okay.
You never have more than one source, or at least this.
Yeah. Yeah, they did just one.
And then multiple detectors.
Yeah, and then
And then
another
and
one.
the next source.
Right, I think I said it correctly. So when you have multiple detectors,
Yes.
how do you map out those multiple detectors? Do you add them together, or how do you consider that?
You have to consider them separately.
So each absorption is scattering for each detector mapped out with that mathematics.
Well, so each detector is just gonna have one measurement.
Right.
Okay, so then you're gonna take all those measurements
Right.
and from that and those equations, then you'll be able to determine UA and
Like a CT propagation, right?
like a what?
CT imaging.
Oh, CT.
In some sense. Right, you have a different kernel. Yeah, it was the transport kernel is very different in light transport than it is for say X-ray propagation. Radon.
So I'll just go briefly over some Monte Carlo solutions using perturbation and differential Monte Carlo. Since we're talking about gradient based, wouldn't it be nice to use a Monte Carlo because it's the gold standard? We can use it close to detectors close to the source. We don't have to worry about optical properties. We can have really complex geometry. So this is a review of what I said last week, where you can determine your model function at a step that you take in your iterative optimization by just reweighting the random walks that you ran for the baseline simulation. So you can store that information, read that database. Aha, I know what my model function prediction is at this new delta A plus delta A. So, of course, reading this database is a lot faster than running an independent simulation. Plus, you don't want to run an independent simulation in a optimization iterative step, or that optimization is going to take a long time to do. The correlation is actually working to your benefit because you're going to get the change to the measurement or model prediction with more accuracy based on the A plus delta A than if you ran a different simulation. And now we have differential informations that we can feed into the optimization, gradient-based optimization. So we did this for a layered tissue, cervical layered tissue, and we're able to recover, we tried to recover the mu-A and mu-S from the top and bottom layers, and we were able to do it with good success with a broader range of mu-A, a third to 3 times, and a smaller range of mu-S, plus or minus 30%. Bless you. So just because I'm going to use this graph in the next set of slides. So we have our measured data. We have an initial guess. We determine chi-squared. Is it converged? Typically not on the first step. Determine an update using your derivatives. Determine your model problem forward prediction based on that step. Determine chi-squared, and keep on going around here until you get your optical properties. So there are other gradient-based algorithms. There's a stochastic gradient descent. So a lot of these options are to reduce speed in your inverse solution. Stochastic gradient descent says, I'm not going to take the derivatives of all the parameters. I'm just going to stochastically pick some of them and use those to figure out my update. Simulated annealing also doesn't always use the gradient all the time. One of the problems with the Levenberg-Marquardt is it can get into what they call this pathological, pathological path, I guess is what it's called. And say you have your chi-squared has a trough, and what's happening is the gradient says, oh, move here. And then here, the gradient says, move here. And you're moving on the ridges of this trough, never getting to the base of it. So to mitigate that pathological path, there's a momentum method that keeps track of previous. So when you get here, it keeps track of, I should finish my sentence, it keeps track of the previous gradients to update your current. So if you're here, you not only know you were here, and it figures out an average so that, it'll help you have more memory of the fact that, yeah, I was here before. Let's take an average and maybe we'll get into this area here. There's also root mean square, where your propagation, where you're keeping the past square of gradients. And this helps when gradients are really high in magnitude. And then there's something called atom, which combine these two. So those are kind of gradient-based alternatives people have done to either improve success of the solution or make it faster. Okay, I'm going to discuss neural nets. Now, I saw that about 5 or 6 of you had machine learning on your charts when you introduced yourself. So I'm going to put it out there that I am no means an expert. I am a student like you. So if you feel free to volunteer your experience of things, I'm going to take a paper that I had access to and show how it was done. So I'm going to define terms enough to describe what was done in this paper, and then I'll describe what his results were. This lab's group's results were. So before we had this Levenberg-Marquardt, and this is the little, you have initial guess, you have a model function, you have your measurement prediction, you put it in, you put it into the chi-squared with your measurements, and then you determine an update. Okay, this is all in with the goal of finding optical properties. In a neural net, Levenberg-Marquardt is often, not always, but often used as a portion of the neural net. And in the neural net, we're not looking for, bless you, optical properties anymore. We're looking for the parameters of the neural net, so the weights and biases of the neural net. Okay, so and then once we've trained the neural net, then we can look for the optical properties. Okay, so I'm going to show a single data sample setup. You have your input, which is fixed. You have your output, which is your training output. That's fixed. And inside here is the makings of the neural net. So you have, say, a layer of neurons here. Each of the inputs gets multiplied by a weight and brought into the neuron, summed, and then gets sent to an activation function, and then moves on to either the next layer. And so all of these get fed into subsequent layers or the output. And then this output gets put into the chi-square. We have the Levenberg-Marquardt over here. So this activation function introduces nonlinearity into the model. Sometimes they use sigmoid, hyperbolic tangent. The key thing is this activation function needs to have a easy derivative, either analytic or just a lot of times they have rectilinear, I think rectilinear units where that's activation function. It's 0 and then y equals x here, which means that the derivative is 0 and 1. Very fast to run it through the activation function and get to the answer. So just to make it simple, let's say we have 2 inputs, we have 2 outputs, we have 3 neurons. So I just wanted to lay out the equations because for me, it just helps me to distill down to something reasonable so I can get my arms around it and kind of contemplate it in an easier way. You have these weights, you multiply them by the inputs, you might add in a bias term here, and then you get a result that gets sent to an activation function that then gets hit with other weights, results in a Z activation function, and gets out these outputs, just to get an idea of how the processing in a smaller dimension. So, and also so that was a single sample. You can create batches. Batches are, multiples of these or portions of these, varies. Epics is when you run through your training set one time, but you have to run through it multiple times to train a neural net. The nice thing is that there's a lot of tools out there that help you develop a neural net really quickly. MATLAB, TensorFlow, Keras. So actually MATLAB actually has a training set for you to use, and you just, you cut and paste the directions, the commands into MATLAB command file, and all of a sudden you're running a neural net, kind of learning by just doing. So I'm going to show the results of somebody who used a neural net to solve a very common problem in biomedical optics. I chose this example for 2 reasons. It's a common problem, like I said. It was performed in the lab of Shenghao Tseng. Shenghao Tseng used to be at BLI, which means that I had access to him and I was able to email and talk to him about what did you really do that you didn't say in your paper. So what he wanted to do is figure out how to determine mu A and mu S prime from two spatially resolved reflectance measurements. Okay, so he had to create his training data first. And he used MCML, this is Jacques and Wang, Monte Carlo code, GPU MCML, runs faster on GPU, and just to create his data set. So he's basically gridded out what mu A and mu S, ranges, and then he divvied it up and he generated, okay, here's the reflectance at these two source detector separations. This is going to form the training set where he wants to feed in these reflectance values and train the neural net to say, I know from these two, I can predict these optical properties. So he created 6,100 sets of training data. He told me which ones, how he divvied. This is all outlined in his paper for the two source detector separations. He used MATLAB train BR. This is Levenberg Marquardt underneath the hood optimization. He used a log sigmoid as his activation function. It's kind of unusual. He used 30 to 80 different number of neurons. He had 2 layers, and he had to vary that based on the source. So he did it for multiple source detectors, but only 2 at a time. So he just wanted to feed in 2 source detector separation reflectance, giving back optical properties, homogeneous. He said it took, the performance only improved slightly after 500 or 600 epochs. This is surprising to me that he had to run that many epochs. So he's taking that training data and just feeds it to the neural net, takes the output of that, feeds it again, sets the training data through, and had to do that. So kind of under the hood, this is what Sheng Hao told me. What he did is he set up a whole bunch of nested loops. He varied the number of neurons, he varied the activation function, he varied the layers, and he just had MATLAB figure it out for him, say, run this, and I think he did for the epochs too, run it, give me the result, and at the result, and also MATLAB puts out a plot of how well are you mimicking back your training data back to you. So he just had it do it. He said that from the time he started creating the training data to actually getting a neural net to give him the right answer took several months. So there's a lot of time involved here. Although a lot of it he let the computer do, and he also put a caveat. He goes, he did this back in 2015. So he goes, it could be done a lot faster. So yeah, that was sure. I am not sure if he made his code open source or not. I have to check. Yeah, I'll check on that. Okay, yeah. Although you have to go further through, aside from the neural net code, you have to go through the work of creating the training data too.
Yeah.
On your own. I have to keep. Yes.
I might have missed how the training data has been created.
So if you can use Monte Carlo with a GPU to create the training data. And he took a range of mu A and mu S, and he figured it out. And he said that all combinations of permutations give me the reflectance at these 2 source detector separations, and then fed the reflectance of those 2 source detector separations into the neural net too, and that the output would be the output. Okay, so you have 2 reflectances, 2 optical properties, but you have them for a variety of optical properties, and then that's one single training set. He synthetically trained with Monte Carlo. Yeah, and he said that just like the lookup table, it's best if you have uniqueness, like you don't want to to the data to map to the two types of solutions to have two UA and US pairs that create the same. Otherwise, the neural net gets confused by it and actually degrades the ability of it to solve the problem. Yes.
You asked him why he uses a log simulator?
Yeah, I know. It's a very weird thing because I have to say in the general literature, log sigmoid's not often used. This is his answer was he tried them all and he just found that this did the best. But the only thing that I might add to it is that I think because neural nets are somewhat new mechanism to solve inverse problems in biomedical optics. I think the other groups that are doing it for like facial recognition, their problems are of a different nature, and maybe that's why their activation functions are as they are. But yeah, it's a funny thing. I don't think I've read another paper that used log sigmoid.
First, I heard I'm wrong. Log sigmoid was used for binary inputs, right?
Binary.
You have something.
I don't know. I don't know. Yeah. Yeah. But I'm pretty sure in the train VR of MATLAB, it offers you. So it's not that out there. Yeah. Yes.
Do you know the percentage of samples that went for the training set? And how many percentage or how much percentage went to the set test or decide how accurate the neural net was?
So he had 6,100 of those sets that he used to train. And then, yeah, he basically determined the performance of the neural net, the final neural net, based on how well he gave that what he knew was gave rise to those two important certifications.
So once he had the model, the neural net,
Yeah.
he classified or predicted the training.
So once he had the neural net all converged and working, then he could put in any two source detector separations and get back the output. Yeah. Yeah. Oops. So I wanted to go through why would you do all these different methods and what are the benefits? You know, if Xinghao is making all of those forward predictions based on a grid of mu A and mu S prime values, why didn't he just use table lookup instead of going through all this neural net? But you have to think of the memory requirements of the lookup table. You have to store all that data, keep it resident, so you can move in and find your inversions. There are memory requirements of a neural net, so you have to weigh those out. A lookup table cannot invert data outside the table well. You can extrapolate, but it may not be correct. Why would you use a model-based versus a neural net? The neural net has a systematic method to obtain the gradient. Gradient is very simple analytic form or just 0, 1 sometimes. Model-based methods need to obtain the derivative of whatever the model is, either analytically or via finite differences. But one of the nice things about a neural net is that it has no idea what's going on underneath the tissue. It doesn't care if it's layered, if there's a tumor in there, which your model would have to take into account. Time to result. Lookup table, all done up front, then you're done. Model-based time is, you know, you have to code up the analytic solution, maybe take the derivative of it, code that up. And neural network time depends on how long it takes you to figure out correct number of layers, neurons, epochs to get the right inversion. So I wanted to talk a little bit about the inverse solution process. Like maybe you have a model that you feel gives you predictions for the right the appropriate measurement that you're trying to invert. Sometimes people just jump right in. They take the measurements. Hey, I'm just going to use this right now with my model and get the exact parameters. But what we've done in Vassan's lab is that we actually take that model and generate simulated measurements. So take that model, put in exact parameters, and use that modeled simulated measurement in your inverse problem. And you better get back the exact parameters back out, because this is just testing your optimization method, but you want to make sure that you're getting exactly, that works exactly. And then you might, maybe you're using standard diffusion. Maybe you might want to simulate your measurements with Monte Carlo, then add some noise, see if you're getting reasonable parameters. So this is kind of your way to step into the problem. Then you might make phantom measurements, and then maybe you'll move to your tissue measurements. So kind of ease in to the problem and start with something you're going to get the right answer. And that just kind of debugs certain parts of your inversion. So I'm going to look at some examples that we ran. And all of this is using the Levenberg-Marquardt. We're going to look at why the types of measurements or the locations of measurements or the noise or the initial guess changes your converged values. So the first one I look at is spatially resolved reflectance. I have 6 detectors. I have a point source here, 6 detectors. I'm trying to find mu A and mu S prime here. I have detectors every 0.1 millimeter out to 0.6. I'm going to simulate my measured data using Monte Carlo with NURBS, with and without noise. And I'm going to use standard diffusion as my model. Okay, so because I'm generating the simulated measurements, I know what optical properties I want to find. So it's a test to the model to see, are you going to be able to find these or not? And, for standard diffusion, my mu S is greater than mu A. So I'm abiding by that assumption of standard diffusion. Okay, so in this plot on the left, I have these row values. This is the source detector separation at 0.1 through 0.6. And in the blue dots are the measured data that I fed the inverse solution. The red is the initial guess. So this is reflectance at those 6 detectors. So this is the initial guess. And then the green is what the Levenberg-Marquardt found. Okay, so we know that it should come to find mu A of 0.01 and mu S prime of 1, but in fact, it found something terrible for mu A, not too bad for mu S prime. And you can see here, this is the chi-squared space for this problem. This is the initial guess, and then this is how it came into this area here. So one of the things you should note is that the measured data, which is 0.01 mu A, 1 mu S, you can't see it, a blue rectangle right here. It's not sitting in this basin. So that's a kind of problem number one. Your measurements aren't sitting in this basin. So does anyone have an idea of why this isn't working well?
What is the model?
Model is standard diffusion. Standard diffusion. So I'm too close. Good one. Bingo. Yeah. So
separation, since if you remember this morning from your slides, you can see that standard diffusion, at least for closer conversion, really does what's happening. It would have to be at least like 1.5 centimeters.
I'll show you. Good one. First time somebody answered it.
We think we would still, we would a. The question is, even so, this fails because standard diffusion is not very good. The question is whether the realistic measure for the cut finite noise, if you have the same vector configuration, you would think that it would.
Well, one of the things you could do is, and I actually exported these from the GUI. Unfortunately, that meant that the font was really small. But in the top plot, I plot standard diffusion at these source detector separations in gold, and then I plot the measured data in green. And see how they're not lining up at the optical properties of the measured. This guy's never guys can never stretch up to here and get it. So now if we move, and I just I just checked this. So L star here is 1 approximately. It's 1 over 1 plus 1.01. So I moved it out 1 L star. So I went to 1, 2, 3, 4, 5, 6 instead as my 6 detectors. And now if you plot the measured data with the model, it's doing a lot better. Standard diffusion is, we're out far enough, it's capturing the measurement at here better. Could be that we need to go a little farther, don't know, but this is what I took here. Okay, now we're looking good. So we have, you can barely see it, we have our measured blue squares down here. Here's our initial guess in red, and then here's what we converge to. And here's the path that we took from this initial guess into this basin. Here's where the measurements lie in it's not exactly in here, right in the, but we still did fairly good recovery, within 20% from UA, 8.4% from US prime. So not bad. Let's add 5% noise. We have 6 measurements, 5% noise. We degraded our MUA convergence and US slightly. So that noise degraded. But these are things you can try as far as seeing how your model deals with these kinds of issues. Then I just took another initial guess because there's different ways you can enter this basin based on the initial guess. And if it's a trough, you want to be coming in from the steepest ways. If you're coming in from the more shallow ways, you want to come in where the gradient is going to be directing you to the basin. So that's a little bit about the initial guesses. Another initial guess. Okay, here I just brought this up because I thought it was kind of a little bit pathological here, but still did pretty good. Gradients. Okay, so now I'm going to go.
Coming in like that, so to speak.
Yeah.
But the initial not
it's not a direct path, but you've got those cross derivatives, right? Right. So if it was all using, like here, it's using, because this is the MUA axis, it's using the MUA information mostly, but then if it's going diagonally here, it's using the cross terms too, right? What do you think? Okay, let's try another problem. We're going to use spatial frequency and wavelength because today's special frequency day, and we're going to look for chromophore concentrations. So I'm going to pick 2 spatial frequencies, 0.2 and 0.3. I'm going to use 8 wavelengths in this range. I'm going to simulate my measurements with NURBS, the Monte Carlo, scaled Monte Carlo, and I'm going to use the model function, the same thing. This is called the inverse crime. It's like, wait, you're using the same thing. That's not a good thing to do because you're just kind of giving back yourself. So let's just do it just because we can play around with it a bit. We're looking for HP and HbO2 and A and B of the power law. So I give the power law here. It's A lambda to the minus B. Those are the coefficients. And these are in micromolar. So I show these. These are what I generated the measured data with. So I know that's what we're trying to find. And then I chose an initial guess just randomly of these. Okay, so just to give you an idea, not a big difference to this inverse solution. It just adds another step. So you have chromophore concentration. We have spectra for HB and HbO2 that we can feed in and get mu A. I think Lawson's first lecture gives a way to determine mu A from chromophore concentrations. And then based on your A and B of your power law, you can get mu S prime. So it's just a matter of having this be part of your model function, and you're just now getting these things out instead of your mu A and mu S prime. Okay, so we're going to be solving for those two. So let's look at what happens with HB and HbO2. So here are our wavelengths. It's hard to see where the measured data are. The initial guess is in red. I think the measured data is underneath. Yeah, it's underneath these green squares here. So, so we started here. We came right in here. We got zero error here, zero error. So, but this is the inverse crime. So of course we got it. So this was just a way of testing. Okay, did we get back what we thought? Yeah. Okay. Let's add 2% noise just for fun. Now, our measurements, you can see now the blue squares are slightly away from the converged values. Here's the initial guess. Here's the start. Here's the end. It's terrible. It's terrible. Just adding 2% noise. Terrible recovery. So here's the power law. Pretty good. We got the A and B coefficients within, less than 2% here. Looks pretty good here. So we're getting scattering, but we're not getting absorption. So why do you think that is? What is wrong with what we're doing? I'll show you. Remember these plots? So I'm using a spatial frequency of 0.2 and 0.3. Okay. This shows spatial frequency reflectance versus spatial frequency here for different, we change absorption. Again, it's using the GUI, modify absorption. You can see spatial frequency 0's got the biggest difference. So it's the most sensitive to changes in mu A. Down here at 0.2, pretty close, 0.3, pretty close. So we're not going to get mu A well with mu S, with fx equals 0.2 and 0.3. However, mu S, pretty separated, even down in this range, looking pretty good. So we're still getting absorption. So let's change. Let's change our spatial frequencies and from 0.2 to 0.3 to 0 and 0.2. Okay, now, and I'll keep the noise. And now we're looking pretty good. We're getting HB and HbO2 pretty well here, less than 2%. And then again, we're getting scattering pretty well here too. So in summary, the aim is to select a type of measurement that's going to pull out the information you need from the tissue, select a model that is valid for what you're trying to pull out and the measurement type, could use Monte Carlo to solve inverse problems. Different optimization methods might help you. And all of the code for the two examples I just showed are in this VTS solver demo. It doesn't create the little chi-squared maps, but it'll create the plots on the left-hand side. So if you wanted to play with it, and plus then you could substitute in your measurements, you could substitute whatever you wanted. So thank you. Okay.
That previous sample.
Yeah.
How much noise? Was the
Oops.
system able to
How much noise can the system handle?
use?
Yeah, I use 2%. Well, that's actually kind of an interesting study. A lot of times, with the noises, like maybe 5%, there's an instrument noise that you might need to add in. And so, yeah, it depends. I mean, it's a nice little study to increase that and see where things start going awry. You can also, sometimes you can mitigate noise by adding more measurements because, right, it smooths out things. But yeah, it depends on the problem and what you're trying to invert and how much that noise is going to affect it. Yeah, for sure. Yeah. But that's the beauty of modeling. You live in the synthetic world and you can play out scenarios and and kind of build confidence until you get to the real world. Yeah.
Scenario that Carole Hayakawa certainly from illustrative purposes. We did 2% noise uniformly across all spatial frequencies. In reality, your noise is probably very small at low spatial frequencies and gets worse at large spatial frequencies. There's also noise floor. So if you want to have more realistic understanding of the impact of the recovery, the effort and then build a realistic noise model for rather than what I would say is simplistic. But the reality is, if you look at a couple slides, yeah, so it's really interesting. If you go back to more, so in the 0.2.3 situation, which is very difficult, you see how the chi-square domain is still nonetheless very smooth and the local variable is unique. And go to the next slide here. You see that the introduction of noise, automatically you actually get two local minima. So noise itself, I think this is really illustrative. Noise can really change the topology of your. It is worthwhile to understand toward in your context. That can then inform where in measurement space we want to actually make measurements.
Okay. Thanks. Oh, was there more? Okay.
I wrote you an email. So
Oh, you wrote me an email? All right. Thank you.
there was something on my mind, but then I forgot, but then I said, so I didn't remember. But
It's private.
yeah.
Thank you so much, guys. We're gonna head on.
Let's go have lunch.
I think Bernard is going to set up meetings. I think a whole bunch of people are going to be one. Is he after? I'll be there.
There is